feedback on if you're done with this chain or not. So basically you post a bunch of messages in here, and then you say I'm done, and you say complete on the blocks. You can also say something like deny forever, I don't remember exactly. And then these blocks start transforming and doing stuff. And all blocks have a task of what state it is in, so you can wait for the completion of the last block if you want to. And then you know that everything has flow through your system. Let's link stuff together. So I'm thinking let's do a buffer and post that into an action block, maybe into a transform block in between, and see that stuff flows through this. So let's start from the beginning. So what did I say? A buffer. We'll continue using like primitives. Of course, you can have as complex types as you want to, but just takes longer to write. We can do something more fancy later on if we got the time. And then we want like the writer. And this will be the block that we made earlier, like console write line. And then maybe we could do like a multiplier. And that we also did earlier, conveniently. We need a return type also here. We can just do it like this, can't we? Yeah. So we start with a buffer and we link it to the multiplier. And then we take the multiplier and we link it to the writer. Okay. And then we will post a bunch of messages. We can do an range again. And then we will post this to the buffer. And then we're done. And we say buffer.complete. And then we can, what's last is the writer. And the completion is the task. All blocks have a completion task, and we can wait for it. Just. So now nothing. Yeah, came out. I didn't almost expect that. Sometimes it's a bit magical. You should, of course, depends what block you're using, but you have these options when you link also, where you have to say that you want to propagate the completion. So if there are any other, there could be blocks in between that are not done. I think it's just so. This one is always if you want to. There are cases when you don't want to propagate completion, but most of the time I want to do that. So that's always nice to have. This will be the same result. Well, there's another kind of cool thing you can do. You can also provide a predicate here. You can say x is bigger than 10. This will only link messages from the buffer to the multiplier if the value is bigger than 10. Maybe we should do 5 instead. But then nothing happens. Why? Because no one took care of the pulled from the buffer before, so it's blocking now. So here we have a problem. We could link to a null target of int for everything below or equal to 5. And then we get the upper. If we just want to throw them away, we could also link them somewhere else. But this is one of the things that I didn't expect, and one of the pitfalls for me. So if you have links, conditional links, you need somewhere to put the messages that you didn't want anywhere. Otherwise, everything just stops. So most of the time when I have had problems with this, it's like the pipeline just halts because it's waiting for a buffer somewhere. So the flow of the messages is really important to keep track of. So that was a fast lap around the pipeline. Some of the stuff I haven't touched that much, and I'm not gonna go into detail into it, I think, is the cancellation. But every options that you saw when creating blocks accepts a cancellation token, just plain cancellation token. So you can like cancel the pipeline whenever you want to, or you can check for that cancellation later in the pipeline. It's quite handy, quite easy to work with, nothing strange. And regarding error handling, a block has a few different states, and one of them can be faulted. If you want to, you can set the block as faulted by yourself, and it will stop sending and receiving messages and unlink itself if it can and stuff like that. Or if you throw an exception, it will do the same thing, set itself to faulted. Since it's parallel, you will have to catch like an aggregate exception in the end and look for the inner exceptions. But it's also, if you've done anything with the task parallel library before, you will feel quite at home. Testing, nothing very fancy. The system we built using this is fully test driven. You can just new up your blocks and you can send stuff to them and you can receive them in a synchronous or asynchronous way. And if you just you can test them in isolation. They're like black boxes. It's nice in that way. And you can test the whole flow and just provide some mock data and write into nothing if you want to. So I would say it's fairly easy to test. You can always, I mean, if you debug and stuff, it's always easy to set the degree of parallelization to 0 everywhere, and then you can debug without problems also. So that's quite handy. So I think we're gonna spend some time doing a little bit of a bigger example, maybe, and connect some stuff. Maybe it will be a little bit similar to the stuff we did, but we could use a little bit more complex, and we could make like a stateful block or something, because we haven't talked about state yet, have we? So I wanted to bring in the domain where we're working to get a bit more closer to reality, and it's a project where we do risk simulations on disasters. So we calculate the costs of maybe earthquakes or floods and windstorms and stuff like that. So in one end of the system, there's lots and lots of math going on and simulations and statistics, and it outputs huge amounts of data. And we then take that data and put together with like presumed contracts for clients. It's like, I want to insure my stuff. And then we calculate, okay, how much risk would it be to take this contract? So we use the terms of the contracts. You can think of it like your own home insurance. You have like a basic fee. If you break something, it costs, I don't know, 1,500. If everything burns up, you don't get more than 800,000 or $1 million or something like that. It's the same terms. The difference is that in these kind of contracts, there are somewhere around 200 terms that interact. But of course, we don't need to do it that complex. But and there's lots and lots of funny things about it. So that's basically what we did. We used the terms of the contracts, and then we calculated the costs of maybe earthquakes or floods and windstorms and stuff like that. And we're gonna do. We're gonna put data about presumed losses into the flow. We're gonna do something with them that we do in real life, maybe scale them, currency converts, aggregate, and do some risk measures on them. I don't know, something easy, and average or a tail value at risk, something not too fancy. So read from this, I think we will skip in the, I was a bit ambitious one late night and read from the actual loss files, but it's a bit too much work. But the steps in general is like read from files, harmonize the data, manipulate it, gather statistics, and write to disk. So now we see this kind of pipeline behavior that this is useful for, actually. And one of the little things that someone mentioned at the end of the project was that, oh, by the way, the data can be like a few terabytes, and you have to do this on one server. So the streaming works very well because we can stream. This is trial-based simulations. So one trial is like this trial, we get these losses for this client. Like the disaster hit them and it costed 2 million for their. And the next trial it cost 1 million. Next time, so we do this like 20,000 or 100,000 times, and then we get the statistics. But you don't need to understand every detail, but it's perhaps valuable to have a real domain. And just to scare you, the specifications for generating the data is something like this. But we don't have to care. We just have to code, isn't it? Right. The original specifications was in like MATLAB, but guys much smarter than me implemented them long before me, and they generate the data. So I just have to consume it and count statistics on it. So I'm glad for that. So let's see. I'm gonna try to, yeah. We're not gonna have enough time to do this all the way through. Let's maybe just do like a skeleton and a stateful block. Something like this. Maybe we can use some of this. The multiplier seems good. Huh? Is that some kind of transformation? And we throw it away. I'm thinking about cheating because I don't have that much time. I will cheat. So something like this we could do. So now we see the patterns as before. We have some kind of join block. You remember I said that we knew. I never said that, but in this case we want 2 data sources. It could be like any number of data sources, but the important thing is it's not just one. So we have use for a joiner, and we have some kind of transformer, and it actually takes these trials that I talked about and it combines them to one signal. And the trial has a number of losses. It's nothing fancy in here, it's just values. And it combines them into a new one. And of course we should check that the items have the same ID or things will blow up. But and then we have some kind of manipulator. In this case we scale all of the losses in each trial down by 20%, just because we think it's a good idea. And then we have a statistics blocks. And we take this joiner and we link it to the manipulator, and the manipulator will link to the statistics block. And then we terminate the flow with a null target. So this is a bit of a more of a complete chain. And then we just cheat a bit and we generate random losses and post them into the two targets of the join block. So this is a bit simplified, but we take, we don't have a whiteboard here, but maybe we can do something like this. You see what I do? Painting by hand. This will end up horribly, but pro stuff. So we have this join block first, on a track mouse pad. So we post our lots of stuff into here. Yeah. Wait, I have a touch screen. I don't know. And then, yeah, this works. Wow. And then we did some manipulation. We joined them, the tuples from here. We took and joined them into something else. So we just have a, and then we did like the scaling, and then we did the metrics or the risk metrics. So this was scaling, and then it was null. Beautiful. So what's important here, or what's interesting, I think, is this metric blocks. I hope you agree with me, because this is a bit of a different beast from the other ones. So the secret to this statistic block, as it's called, is it's a custom class. So there's nothing fancy about that, but it contains a transform block and a values list. So this is the state. This is my state. So this one is extremely important. Otherwise it will really mess up my state, or we could do some locking or concurrent something. We have to do something. We can't just leave it as it is. So every trial will flow through this, and we will just take the total and the max loss. So it's like aggregating everything into small, the compressed data, the max value and the total value. And then we can return the average of all values, or some other statistic on those values. So it's not very complicated, but you have to do it your own, or wrap the blocks to get this. So I don't know if it works. Let's try. Yay! The demo ghost. Anyway, the important thing is that that you got the takeaway is the statistic blocks. I mean, with a state inside. I have lots of fancy stuff and not that much time left, so I think I'm gonna leave it at here. And if you want to see some more complex examples, I have examples where I actually stream the data live from disk and stuff like that. I'd be happy to show afterwards. But I have a few small slides left. So the learnings. Single producer constraint is one of the options, and it's extremely important. It tells a block that there will only be one source of data to these blocks, and then the TPL Dataflow Library optimizes away lots of synchronization code and stuff, so it's speeded up our application considerably. So as long as you don't have multiple blocks posting to one block, you can always use this. Queues can overflow. If something produces lots of data and you can't consume it in time, the queues are unbounded by default. So the solution there is to set them to like a max, and maybe instead of post, you can send async and await those, and it will throttle. And we used a really cool thing that I want to show at the end to visualize these flows. It's called WebWiz. Has anyone seen it? It's VisGraph. GraphVis is like a graph language, and you take strings and you generate graphs of different kinds. So we actually, in the live system, we have orchestrator that constructs our chains for the calculations, and then we have a chain visitor that goes and gets strings for what got constructed. So if we take something like this, we can get the real-time output of what actually is done, and we can get this like a visual. No one said anything, but why not? So we can self-generate a description of our flow, and we can visualize it and talk with the business about it and have test cases. So that's really cool. So this is like on a high level, and of course on a much uglier and more technical debugging level, you can get every single little block, and an actual flow might look as like this. So these are all blocks, and how it flows through them, and how it branches out and in, and stuff like that. So it's really handy, and it's quite cool. And you can also inject debug blocks between them. Just copy the data and output it, so you can see exactly monitor what happens in your system. So that's a recommendation to do something like that. And of course, build your own little wrapper, because I don't personally like the link to stuff. We built a kind of a more DSL around them. If you can make this look way much nicer. You could also make this look like this with the blocks, just with a few extensions methods and stuff, and build your chains in a nicer way, declarative. So that's also a recommendation from me. So that's about everything. Thank you very much.